So welcome to this segment as we continue to look at specific latent heat of vaporization. Now you remember from our previous discussion when I started looking at latent heat, I did simply say that heat that is absorbed during melting or boiling without change in temperature, and that is what we called as being latent heat. So that is what we called as being latent heat. But today we want to focus on specific latent heat of vaporization. What exactly is specific latent heat of vaporization? Of course, I use that symbol L and a small v, but some books they may use just a small letter L there. Well, when we talk about specific latent heat of vaporization, we can simply say is the amount of thermal energy required to change a unit mass. Like we say, the unit mass is 1 kg, from liquid to gas at constant temperature. So this is what we can call as being specific latent heat of vaporization. So the amount of thermal energy that is required to change a unit mass, the 1 kg from solid to gas at constant temperature. In other words, it's the amount of thermal energy that is required to change a unit mass, to change the phase of a unit mass. But of course, that is going to take place at constant temperature. That is what we're talking about. So when you want to change a liquid and you want to change it into a gas, remember this is normally what we simply call as being boiling, and if you are going backwards there, that is what we call as being condensing or condensation. So now what is going to happen? The amount of thermal energy required to change, in this case that liquid to gas or from gas to liquid, that is what we call as being specific latent heat of vaporization. So remember, it is simply just the same. There's actually nothing different. So now when boiling is taking place from liquid to gas, remember that thermal energy is actually absorbed. In other words, we can say latent heat is actually absorbed. And when condensation is taking place, you're moving from gas to liquid, we are simply saying that latent heat is released. So in this case, it is released. But of course, the energy that is needed to change a liquid to gas or a gas to a liquid is just going to be the same. It is not going to be different. So the formula that we apply in order to calculate that is that, for example, if you want to calculate the thermal energy, so we simply say the thermal energy or the heat energy, remember, like I said, E is equal to simply the mass multiplied by what we are calling as being specific latent heat of vaporization. I've just abbreviated that. So that is to say, the thermal energy will be equal to the mass. Remember the symbol in this case, that is, LV if you want L. Now, it is possible that we can know this specific latent heat of vaporization by making, LV the subject of the formula. So when we make LV the subject of the formula, it simply means I'll divide M. What I do this side, I'll do it the other side as well. It simply means that specific latent heat of vaporization will be equal to the thermal energy that is absorbed or released, depending on what you are looking at. Is it when you are changing from liquid to gas, or is it from condensing from gas to liquid? So you divide by the mass. Now, of course, you remember energy is measured in joules. Our mass is in kilograms. So therefore, you are going to have joule per kilogram. So the unit in this case for specific latent heat of vaporization is simply joule per kg. So that is what we mean there. So you need to remember, this formula here. You need to remember it. But of course, when you want to calculate the energy, you need to remember that energy, when you are changing the phase, in this case it's mass multiplied by specific latent heat of vaporization. Now let me just illustrate it kind of this way. Allow me just to clean up this section so that I can just illustrate it. Imagine that you have got a 1 kg water. You have got 1 kg of water that is at 100 degrees Celsius, and you want to change this 1 kg of water that is in liquid form to 1 kg of steam, but still at the same temperature of 100 degrees Celsius. So that's what we mean. So the energy that you need in this case there, so we are calling that one as being the specific latent heat of vaporization. So you want to change 1 kg of water which is in liquid at 100 degrees, and to change it to still 1 kg, but change it into steam, meaning it is now going into gaseous form but still at that one. So the energy that you need is what we are calling mass multiplied by the latent heat of specific latent heat of vaporization. Now the value for the specific latent heat of vaporization, if you are dealing with water, these are all measured. Different liquids have got different specific latent heat of vaporization. In the case of when you're changing water to steam, it is about 2.26 times 10 raised to the power 6 joules per kilogram. So that is the value that you'll be given. But of course in the exam you are all going to be given all this stuff. So in summary, remember that when you are changing state, it could be that you are moving from solid going into changing into a liquid, or from a liquid going into a gas, or it could be the other way around. Of course, we know from solid to liquid, we know that is actually melting. From liquid to gas, that is actually boiling. And from gas to liquid, that is condensation. And from liquid to solid, that we may call as being freezing. So now in each case, here you have got latent heat that is absorbed. So in this case, remember when you're going in that direction, the latent heat is actually being absorbed. And when you're moving in that direction, you are going from gas to solid, you are going to find that latent heat is going to be released. So in this case, you find that latent heat, released. Okay. And of course, when you're going in that direction, we are simply talking about latent heat, absorbed. So the latent heat needs to be absorbed. But I want to remind you, something that we did talk about. When you're changing in this case from solid to a liquid, that is what we call as being specific latent heat of fusion, which is the same as when you're changing from liquid to solid. It's specific latent heat of fusion. So you don't need to forget, the value is the same. But in this case again, when you are changing a liquid to a gas, that is what we are calling as being latent heat of specific latent heat of vaporization, which is the same there. So the values are going to be the same. So don't confuse them. They are all latent heat, but when you're changing a phase, so when you are changing a phase from solid to liquid or vice versa, that is a specific latent heat of fusion. When you are changing a phase from liquid to gas or gas to liquid, that is specific latent heat of in this case vaporization. That is why we said if you want to calculate the energy there, remember the energy E is equal to mass and specific latent heat of fusion. But there, if you want to calculate, in this case, the energy that you need to do that, remember we did say for that, the energy is equal to mass times the specific latent heat of fusion. So you don't need to forget that. All right, so now I want to show you some few examples that you can just look at and see how you can actually get to apply this concept. Please try to pay attention so that I can guide you properly. You need such content to understand. So I've got two questions that I want to illustrate, very important questions. Just pay attention. The first one there says that what would be the latent heat of vaporization. So they want us to find the latent heat of vaporization of a liquid turned into a gas by heating a liquid with 30 kilowatt, that is the power, for 2 minutes. Then the mass of a liquid is that. So if I look at question number 1, what is the data that we do have there? They have given us, in this case, the mass of the liquid is actually a 3 kg. They have given us the power, which is 30 kilowatt. But you remember, you need to convert that to watt by multiplying by 1000. So that will give me 30,000 watt. Then for the time, you also need to convert it to the SI unit. They have given us 2 minutes. So you just multiply by 60, which will give us 120 seconds. All right. So that is what they want us. So the question says we calculate the latent heat of vaporization. So that is the one that we want to calculate. So the first thing that you're going to do, you need to calculate how much, how much energy was being supplied. So in this case, energy, because you have the power and the time, is equal to power times time. Remember what I told you. So the power there is equal to 30,000 watt multiplied by the time, which is 120 seconds. So therefore the energy in this case, so we can just multiply that. So it is going to be 30,000 multiplied by 120. That is going to give us that is going to give us okay, that is 1 2 1 2 3, right? So that is going to give us 3,600,000, and that is going to be in joule. Right, so once you calculate that, we can calculate that by applying the formula E is equal to the mass and the specific latent heat of vaporization. But remember, VL, when I make subject, it will be the energy divided. Let me just put it in this direction. So our LV will be equal to the energy divided by the mass. So what's the energy? It is that energy that you have calculated there. So in joule, and divided by the mass, it was actually a 3 kg. So what is that going to give us? So when you get that value there divided by 3, it is going to give us 20. Okay, then right, 1 2 3. So 1 2 3 4 5. All right, this is what we're having. So that is going to give us, in this case, a 1,200,000, and that is going to be in joule per kg. So this is what you needed to do there. So basically that's the way you could have calculated that one. So very simple, not complicated. Let's try to look at the second one. Please pay attention with the second one. It appears to be a bit tricky, but it's a very simple question, so pay attention with that. So it says that a pan contains 20 kg of water at 0 degrees. So 20 kg of water, which is at 0 degrees. Then a jet of steam at 100 degrees. So remember, they're talking about steam at 100 degrees is passed through the water. What is the temperature of the water when 0.1 kg of steam have condensed in it? So I love to put up just an illustration that can actually help you. So what we can do is that maybe I can illustrate it this way so that you are able to see what I'm talking about. So there are two things that I have here. I have water that is at 0 degrees Celsius, and of course the mass of the water from the question there is actually 20 kg. So that is what they have given us there. So the mass of the water is equal to 20 kg. Then what are you having there? You also have steam. In fact, you do have steam, which is at 100 degrees Celsius. And what is the mass of the steam? It is 0.1 kg of steam. So that is what we have actually been given. So if that is the case now, that we are having there, how are we going to do it there? So how are we going to go about it? So now according to the question, remember the steam was fired or was actually passed through the water. So meaning that what is going to happen is that the temperature of the steam is actually going to drop. So the temperature of the steam will drop, then the temperature of the water is going to increase, and therefore you are going to get a final temperature. Let me call that final temperature, which I don't know, as being theta. So let me just call it in this case as being the final temperature that we are going to have. Now remember, in this case, what you need to do there is that, because this is steam, you need to change from steam to water. So you need to change to 100 degrees of water. So meaning for you to change from steam to 100 degrees of water, you need energy, and that energy is given by mass multiplied by latent heat of vaporization. Then again, what is going to happen there, or what is going to happen, you are going to change again. You need another energy that is going to be lost. Energy again, sorry, is going to be lost in this case. So here you are losing energy. Their energy will be lost again from 100 degrees of water to reach this final temperature, but that energy will be given by mass, specific heat capacity, and the change in temperature. But what about in this case? Well, you just need to change from, because this is water, you just need the energy, that will be gained to bring the temperature to that. So therefore, the energy will be equal to mass, specific heat capacity, and change in what? Change in temperature. So we are going to use these analysis so that we can actually look at them. Let me call that one energy 1 that needs to be lost, and that will be energy 2, and let me call that one as being energy 3. So how do we calculate in this case what is the temperature of the water? So assuming no heat is lost or absorbed by the pan, and they have given us that data. So from this information that I've actually given you, what we are going to do is that when I look at energy 1, or let me give you this simple analysis, you need to remember that thermal energy, the thermal energy lost. So the thermal energy lost, in this case, what is losing the thermal energy? The steam is actually losing energy. So once that thermal energy is lost, it is equal to the thermal energy that is gained. And what is gaining the thermal energy? It is the cold water in this case, which is at 0 degrees. So as the steam loses the thermal energy, the water gains that thermal energy, and thereby the temperature of the water will increase, the temperature of the steam will reduce. No wonder I'm saying let our final temperature be theta, at somewhere in the middle there. So meaning the thermal energy that is lost, remember, will be equal to energy 1 plus energy plus the energy 2. This should be equal to the energy that has been gained by the water, which is equal to energy 3. And if you remember the formulas, I'm just going to replace them there, and we do our calculations. Let's try to see how that is going to be. So we are saying in this case, the energy lost, so E1 plus E2 should be equal to E3. So that's what we mean. So E1 was simply given by mass and latent heat of vaporization plus the mass, in this case heat capacity, and change in temperature, which should be equal to, in this case, the mass, specific heat capacity, and change in temperature. So remember the diagram that we had in this case. So you had 100 degrees, so that was steam, but of course you need to come to 100 degrees of water. This is our final temperature we want to find, and there you have 0 degrees there. That is what we have. Please don't confuse yourself. Let's just go together so that you are able to basically get to understand this scenario that we are looking at. Okay, so that is what is. So my mass there, if you look at my mass, in this case this side is for the steam and this side is simply for the water. So the mass of the steam was what? It was 0.1 multiplied by LV, the specific latent heat of fusion, that's the value, 2.26 times 10 raised to the power 6, right, plus my mass, 0.1 times the specific heat capacity, in this case for water, which is, they have given us 4,200, multiplied by the change in temperature. So what would be the change in temperature? Did you notice the change in temperature? So the change in temperature there, you know, when it is water, to bring it to that temperature, remember the change in temperature is going to simply be given by 100 degrees minus this theta there. So it is going to be, in this case, you know, 100 minus, you know, theta. So that is what we are going to have there. That will be equal to, let me use a different marker. So that will be equal to, what is the mass of the water on the other side? We said it is 20, specific heat capacity 4,200, and the change in temperature. Now if you notice the change in temperature there, you are from 0, so theta minus 0 will just give you theta there. That is what you are going to have. So we can just multiply that, so it will be 0.1 multiplied by 2.26 exponent 6 there. Okay, so it is going to give me a value that I'm having there, 226 and 3 zeros. So that is going to give us a 226,000, plus if we multiply that is 0.1, so 0.1 multiplied by 4,200, that is going to give me a 420, and that is going to be 100 minus you know, theta, which should be equal to, allow me to just clear up this so that you are able to see. So if you multiply that 4,000, you know, 4,200 multiplied by, you know, 20, all right, so multiply by 20, 1, 2, 3, right. So in this case, sorry, this should have been just a 2 kg there. Take note of that. This should have just been a 2 kg. So my mass there is just supposed to be a 2 kg for the water, nothing more. So when you multiply that, it is going to give you a 8,000, you know, 400, and that would be, you know, theta. That's what we are going to have. So what we can simply do is that if we want, this can go the other side. There's actually no problem with that. So you're going to find that we have 420, then that would be 100 minus theta is equal to, that would be, you know, 8,400 theta minus, okay, so sorry, we cannot actually add the 2, so let me just try to expand that. That's a wrong mathematical expression. We can expand that. So when I expand that, it is going to be 2260 plus this times that will give me, just add 2 zeros there, so add 2 zeros minus 420 times theta will give us 420 theta, which is equal to 8400 and the theta there. So now we can put up the like terms. These are like terms, therefore they can be added. 226,000 plus 42,000, so we can have our 42,000 there. So that is going to give me 268,000, which is equal to, so this will go the other side, so it will be 8,400 theta plus 420 theta. So what is that going to give you? 268,000. When you add that, 8400 plus 420, it is going to give you, it is actually going to give you 8,820 theta. So how do I find theta? I'll divide, in this case, 8,820. What I do the other side, I'll do it also the other side. So remember, you just need to do your mathematical gymnastics. So if you get the value 268,000 divided by 8,820, you are going to find that it is going to give you to 1 decimal place. I can simply say that will give us a 30, 0.4 degrees Celsius. So that is the temperature that is going to be there. So this is the way you needed to go about it. Well, it looks complicated, but please just try to take your time so that you can go through and understand what is happening there, just like I explained there. Then you'll be able to do such a question. Thank you so much for watching. I'll try to do some more practice questions, especially on this one, so that I can help you in future, just to become familiar with that. Thank you so much for watching my video.